So in the last few lectures, discussed about the eigenvalue problems and Cayley-Hamilton theorems. Discuss about the eigenvalues of some special reals and a complex matrices. So in a real matrices, we will discuss about the symmetric, skew symmetric, and orthogonal matrix. What is the symmetric matrix? Any idea what is a symmetric matrix?
Matrix, it is
Yes.
So
equal
A transpose is equal to A for a symmetric matrix.
Okay. So any square matrix of order n cross n said to be a symmetric matrix if A is equal to A transpose. Okay. A is equal to A transpose. Is it visible? The PPT is visible to you?
Yes, sir.
Yes, sir.
So you can see, so if A is a real n cross n matrix and A transpose is equal to A, yes. So if A is a real n cross n square matrix and if A transpose is equal to A, the matrix A is called a symmetric matrix. So A transpose is equal to A. So what does this means? So I jth elements of A that is equal to a j ith elements for all I and j. Okay. Then A is called a symmetric matrix. For example, you can see suppose the diagonal elements are the -1, 2, 4. Then if 1, 2 element is a 1, then 2, 1 is also equal to a 1. If 1, 3 is equal to -2, then 3, 1 that is also equal to -2. Means I jth elements is equal to j ith elements. Okay, so now here 2, 3 elements is a 5, then 3, 2 is also 5. So it is a symmetric matrix. It will satisfy the criteria Aij is equal to a jith elements. Ijth element is equal to a jith element. And if you will calculate its transpose, so it is equal to a matrix also. Now, skew symmetric matrix. Okay, I hope you know what is a skew symmetric matrix. So, is real square matrix is said to be a skew symmetric if A transpose is equal to a minus of A. A transpose is equal to a minus of A. So now here you can see one matrix of 3 cross 3. That is -1, 1, 2, -1, 2, 5, 2, -5, 5. Is it a symmetric matrix? Yes. Is it a symmetric matrix?
No, sir.
Why? Yes. As per definitions, A transpose is equal to a minus of A. So what does this mean? ijth element, that should be equal to a minus of the jith elements for all I and j. Okay, so this is true here. So if 1 2 element is a 1, then 2 1 is equal to a minus 1. And if 1 3 is equal to a minus 2 here, then 3 2 should be equal to a 2. And that is true here. So 3 1 3 1, that is also 2 here. And if 2 3 is here is a 5, then 3 2 should be a minus 5. That is also true here. Then why it is not a skew symmetric matrix? What's the reason? Yes. Why it is not a skew symmetric matrix? Hmm? Batao.
So it is a skew symmetric matrix as A transpose is equal to minus of A.
It is a skew symmetric matrix. Okay, because it satisfies this criteria. Okay, A transpose is equal to a minus of A. Okay, but from this Aij is equal to minus Aji. Okay, then as per this definition, what should be the diagonal entries of the skew symmetric matrix? Diagonal entries I is equal to a j. So it means Aii is equal to a minus Aii. So that means 2Aii is equal to 0. This implies Aii is equal to 0. Is it clear? So the diagonal entries of the skew symmetric matrix, they should be a 0. That is equal to a 0. Okay, so note here this criterion for a skew symmetric. So it implies for a diagonal entries. For diagonal entries, I should be equal to a j. That is, I should be equal to a j. Okay, so therefore Aii that is equal to minus Aii. So this implies 2Aii is equal to a 0. Implies Aii is equal to a 0. So what does this mean? The diagonal entries of the skew symmetric matrix, they should be equal to a 0. So this matrix is not a skew symmetric matrix because here diagonal entries are non-zero. Diagonal entries are non-zero. So that is the remark here. You can see the remark, the diagonal entries of the skew symmetric matrix are always 0. Second, every square matrix can be expressed as an important point. Every square matrix can be expressed as a sum of the symmetric and skew symmetric matrix. Every real square matrix can be expressed as a sum of. So suppose A is the real square matrix. We can rewrite it as equal to a B plus C, where B is a symmetric matrix and C is a skew symmetric matrix. Got it? So now where B is equal to 1 by 2 A plus A transpose. Now, if you will calculate the transpose of a B matrix, you will get it is equal to a B matrix. That means B is a symmetric matrix here. Okay, and C should be equal to 1 by 2 into A minus A transpose. Okay, if you will calculate C transpose, you will get it is equal to minus of C. Minus of C. So It means every real square matrix can be expressed as sum of the symmetric and the skew symmetric matrix. Then what about the eigenvalues? Okay, so the eigenvalues of a real symmetric matrix are always real. Okay, they are always real, and eigenvalues of a skew symmetric matrix are zero, purely imaginary, pure imaginary. Yes. I with the example. Okay, so let A the um, given matrix. You have to show that A is a symmetric and also verify its eigenvalues are real. So on the question, find out its eigenvalue. Very calculator this. So first, you should calculate A transpose. And here in this case, you will calculate A transpose. I hope you know how to calculate. So you can put the row into a column. So first row will become the first column, and second row will become the second column. So again, you will get the same matrix A. So A transpose is equal to A. So therefore, A is a symmetric. Okay, and now find the eigenvalues. So write the characteristic equations of the A matrix, that is the determinant of A minus lambda is equal to a 0. So now you will get here the second degree algebraic equations in a lambda. Okay, so that is lambda square minus 6 lambda plus 8 is equal to 0. So which implies that lambda is equal to a, no, what are the roots of this algebraic equation? That is the 2 and 4. So its eigenvalues are 2 and 4, which are real. Okay. So if your matrix A is a symmetric matrix, then its eigenvalues are real. Now, can you find out its eigenvectors? For lambda is equal to 2 and lambda is equal to 4, you should find out the eigenvectors. So now eigenvectors for lambda is equal to 4, that is a 1 1 transpose. And eigenvector for lambda is equal to 2, that is 1 minus 1 transpose. I hope you can calculate this now. So these two vectors, the eigenvectors, they are orthogonal to each other. So what do they mean by the orthogonals? Two vectors are said to be orthogonal if their inner product, or you can say with a dot product in case of one vector. Okay, so if their inner product, it is denoted by this. B1 and B2 are two vectors here, eigenvectors. So their product, so that is equal to a 0. How to calculate this inner product? Like dot product. The first component of B1 is multiplied with the first component of B2, that is 1 into 1 plus second component of the B1 is multiplied with the second component of the B2, that is a minus 1. So you will get it is equal to a 0. 1 dot 1 plus 1 dot minus 1, that is equal to 0. So therefore, B1 and B2 are orthogonal to each other. Okay, so they are orthogonal vectors. So eigenvectors of this symmetric matrix, they are orthogonals. Okay, they are orthogonals to each other. Now, what is the orthogonal matrix? Square matrix A is said to be orthogonal if A into A transpose is equal to a identity. Okay, so what does this mean? The inverse of the A matrix that is equal to a. So what does this mean? Inverse of A matrix is equal to A transpose. Then your matrix A is a orthogonal matrix. Then your square matrix A is a orthogonal matrix. Got it? So these are the type of the real matrix. So orthogonal, a real square matrix A is said to be orthogonal if A into A transpose is equal to identity. means A inverse is equal to A transpose. Now we have one theorem also. The square matrix is orthogonal if and only if the row or a column matrix form an orthogonal set of vectors. Okay, and theorems about the eigenvalues. The eigenvalues of the orthogonal matrix are real or a complex conjugate in pair and have the absolute value 1. The eigenvalues of orthogonal matrix, they are either real or if they are complex, then they will occur in a pair. Okay, if one is a alpha plus iota beta, then second is a alpha minus iota beta. Okay, so now let's take an example so that the matrix A is an orthogonal matrix, and also verify that the absolute value of eigenvalue of A is a 1. Can you examine that it is an orthogonal matrix? Can you check it is an orthogonal matrix? If it is an orthogonal matrix, then A into A transpose, that should be equal to a I, or A inverse of this matrix, that is equal to a A transpose. So calculate the A transpose for this matrix. What is the A transpose? Then multiply the A transpose with the A. So here I have calculated this A transpose and then calculate A into A transpose. A into A transpose, that is equal to this identity matrix. Okay, so therefore A is an orthogonal matrix. Okay. Also the set, this column vectors, they are orthogonal set. Okay, so they are orthogonal set. Okay, so means the dot product of any two vectors, these are the column vectors in an A matrix. In an A matrix, this is a column vector 1, sorry, row vector 1, this is a row vector 2nd, this is a row vector 3rd. Okay, you can check here. This is a first row vector 1 by under root 2, 0, 1 by under root 2, second is a 0, 1, 0, third is a 1 by under root 2, 0, minus 1 by under root 2. So the set is V1, V2 and V3. So these are the 3 row vectors, okay, of a matrix. They are orthogonals. Means the dot product of any two vectors, that is equal to 0. You can check this. If you calculate the dot product of any two vectors, then it is equal to a 0. Now find out the eigenvalues of A matrix and prove that the eigenvalues are either real or a complex conjugate in here, and have the are real or complex conjugates in a pair and have the absolute value 1. So now if you will calculate here, these are the eigenvalues. You will get as characteristic equations. Lambda minus 1 into lambda square minus 1 is equal to 0, which implies that lambda is equal to 1, 1 and minus 1. The matrix A has real eigenvalues. Okay, so this matrix has a real eigenvalues with absolute value, because if you will calculate the absolute value magnitude of each eigenvalues, that is a 1 absolute value or a magnitudes of each eigenvalue. Okay, so that is the determinant here of each eigenvalues. So each eigenvalue has a determinant value, modulus value that is equal to a 1. So that is the absolute value. So this is true here. So the eigenvalues of orthogonal matrix are real or complex conjugate in pair and have the absolute value 1. Is there any questions here? Yes. Any questions?
No, sir.
So next is the Hermitian matrix. So now this Hermitian matrix is a generalizations of the symmetric matrix from real to a complex number system. Okay. So if A is a square complex matrix, is said to be a Hermitian if A conjugate transpose is equal to A conjugate transpose is equal to A. That is Aij is equal to Aj conjugate. If it is a real, then conjugate of Ji is equal to a Aj. Conjugate of Aj is equal to a conjugate of Aj. So this is the generalizations from the real to a complex number system, from symmetric to a Hermitian. So now this is true for all. Okay, so what this means now, let's take an example. Example are 6. Suppose these are diagonal entries and of diagonals, suppose A12, that is a 2 plus iota, then A21, that is equal to a conjugate of this, that is 2 minus iota. Is there any criteria on the diagonal entries of a Hermitian matrix? Aij is equal to Aj conjugate. So is there any criteria? Any conditions? Yes? Hello? You should examine here. There should be a
The
real.
imaginary part should be 0.
How can you prove this? From here, na? This is the criteria for a Hermitian matrix. This is the criteria for Hermitian matrix. Now suppose if A I J is equal to suppose A plus iota B, I will write. Then this AJI conjugate so Aij is equal to A minus iota B, cancel out, 2 iota B is equal to 0. This implies B is equal to 0. Okay, so in Aij, so B should be equal to 0. Then this Aij is equal to Aji conjugate is equal to Aji conjugate. Okay. The meaning, na? Because this also implies Aij conjugate is equal to Aji. Okay, so suppose Aij is equal to this, then what is the Aji? Aji, that is the conjugate of Aij. Okay, and as per this criteria, you will get these equations. A plus iota B is equal to A minus iota B. So this implies B is equal to 0. So if B is equal to 0, so therefore Aij is equal to A. It means it is a real. So diagonal entry should be a real. So they are real here. And this skew symmetric skew Hermitian matrix, which is the realizations of the skew symmetric matrix from a real to a complex number system. So the criteria is a square complex matrix is said to be a skew Hermitian if it will satisfy this criteria. A conjugate transpose is equal to a minus of A. That means Aij is equal to minus of Aji conjugate. Then what should be the diagonal entries? So the diagonal entries of the skew Hermitian matrix should be a purely imaginary. Na? Okay, 0 or purely imaginary, you can say. Okay, you can similarly you can prove this now. So A will be this A will become 0 by this criteria. Okay, so Aij will become iota B. So it is purely imaginary 0. So every now square complex matrix can be expressed as a sum of the Hermitians and a skew Hermitians matrix. Like real matrix, uh, uh, they can be expressed as a real square matrix can be expressed as sum of the symmetric and a skew symmetric matrix. So in case of a skew Hermitians matrix, the square complex matrix can be written as the sum of the Hermitian and skew Hermitian matrix, where this Hermitian matrix B is equal to 1 by 2 A plus A conjugate transpose, and C matrix is equal to 1 by 2 A minus A conjugate transpose. Now, what about the eigenvalues? Okay, so eigenvalues of the Hermitian matrix are real, and the skew Hermitian matrix are 0 or purely imaginary. So, you find out the eigenvalues of this A matrix, second matrix. Okay, so first you have to prove that this is the Hermitians, and then find out its eigenvalue. Arif, find out the eigenvalue. Yes, you have to prove that this is the Hermitians matrix. So for that you should calculate A conjugate first of this matrix, then conjugate transpose. So if A transpose conjugate is again equal to A matrix, then it is the Hermitian matrix. If it is a Hermitian matrix, then find out its eigenvalues. Yes. Okay, if you will calculate its eigenvalues, so see the eigenvalues are real because it is the Hermitian matrix. Did you calculate for this A matrix? Yeah, we have to calculate. Mathematics is understanding and practice. I know maybe these concepts are very simple for you, okay, but if you will do this practice now, so your calculation will become fast. It's very important in mathematics. You will tell me the value. The time I will click your attendance. And I will tell you the next matrix. Calculate the eigen. Prove it is a Hermitian and then calculate its eigenvalue. Who is present? ये आपने calculate? You present there. Hello. Yes. Okay. So if you will calculate, I hope so you have done this. If you will calculate its eigenvalue, so you will get the eigenvalues are real in this case. Okay. So next is the unitary matrix. So unitary matrix, that is the extension of the orthogonal matrix from the real to a complex number system. So a square complex matrix is said to be a unitary matrix if A into A conjugate transpose that is equal to identity matrix. Is A inverse is equal to A conjugate transpose here. Okay, and it is also equal to A conjugate transpose into A. So, for example, this A matrix. So this is your unitary matrix. If you will calculate A conjugate transpose for this matrix and multiply with this matrix, you will get it is equal to identity matrix. Okay. What about the eigenvalues of unitary matrix? The values of a unitary matrix have an absolute value like orthogonal matrix. So there value also have an absolute value or a magnitude is a 1. And what is a normal matrix? A square complex matrix A is said to be a normal matrix if it will satisfy this criteria. A into A conjugate transpose is equal to A conjugate transpose into A. Okay, so if it is equal to identity, then it will become the unitary matrix. And if it is not equal to identity, then it is a normal matrix. So it means every unitary matrix is a normal matrix. Okay. The Hermitian, if you will check, the Hermitian matrix is also a normal matrix that will also satisfy this criteria. A into A conjugate transpose, A conjugate transpose into A. So these are the some type of real and complex matrices. To remember their eigenvalues. In some examples, and we have a proof here. We have calculated eigenvalues in case of this orthogonal matrix, and we got that their eigenvalues, their absolute value is of 1. The value of eigenvalue is of 1. Okay. Similarly, you can prove for emissions, Q emissions or a symmetry also. Okay. If you have any doubt, then you can ask the question. Any question? Leave the class. If you have any questions, then you can ask.